Okay, in order to write a pattern in sigma notation, you need the sigma and your initial, whatever that is, and the last number that goes up here. So this is what you start at, this is where you finish, this is where you start, and then you need the pattern here. Now, that means we're going to have to find a pattern on these numbers here. The easy pattern to see is that on top you're just adding 1 every time, and on the bottom you're also just adding 1 every time. So a pattern like this is easier if you break up the top and break up the bottom, since you know that since you know the pattern on top and you know the pattern on bottom pretty well. So if I look at just the top pattern, looks like 1, 2, 3, 4, and so on. That's easy. That means the top has a pattern of just n. Because whatever value it is, this is the first term has 1, second term has 2, third term has 3. Notice the bottom almost has the same one, except that it starts at 2 and adds 1 every time. So it's going to look like 2, 3, 4, 5, and so on. So instead of having just n, basically on the bottom you would have n plus 1, since you're always 1 more than the top. So the pattern we have here is n over n plus 1. So we can start to write our sigma notation. So now the question is, what value, what n value am I starting with? I already said that I'm starting with 1. I think that's the easiest one to pick. And just to double check, let's see if that actually is true. If I plug in 1, if I equals 1, I would plug in 1 over 1 plus 1, which would give me 1 over 2, which is my first term. So that's correct. The question is, where do I stop? What n value goes here? So if you look, let's try, it looks like it might be 9 since it's just 1, 2, 3, all the way up to 9. So I'm going to try it. Let's try 9. If I equals 9, I'm going to plug in 9 over 9 plus 1, which is 9 over 10. And that's correct. So this right here is your sigma notation. So again, you start with some value for I or n, and then you have a pattern, and then you need to find the last I value that it'll finish at. Oh, small mistake. If I equals 1, then that's the value that needs to be changing every time, so it actually looks like this. Number 2, same thing again, sigma notation. So basically I need to find the pattern. One easy thing is that each one of these has 2. That doesn't seem to be changing. So as far as the pattern goes, I know I will have 2 there. If this is the first term, I have the first term squared, second term squared, third term squared. So this is just my increasing 1, 2, 3, up to 9. So this looks something like I squared. The squared, notice how the squareds stay the same the whole time. So this seems to be my pattern. All I have to do is start to plug it into the notation, 2 I squared. looks like I might plug in 1 here. Let's double check. I equals 1, 2, 1 squared, which, if I look right here, is exactly what I have there. So that seems to be good. Then 1, 2, 3, all the way up to 9. Looks like I'm going to end at 9, just to double check. 2, 9 squared is exactly the same pattern. Number 3, another sigma notation. I can see right away that this is going to be that type of problem that's called alternating, since it goes from minus positive to negative to positive to negative to positive and so on. So I'm going to have to keep that in mind. This one's a pretty obvious geometric sequence, since it goes from 1 to 1/3 to 1/9 to 1/27. So hopefully you can see that this is geometric, where the ratio is just 1/3. Now, that's not entirely correct, since it's going negative, positive, negative, positive. The ratio you're multiplying is always going to be negative 1/3, because negative times a negative becomes positive, times a negative is a negative, times a negative is a positive, and that would create an alternating sequence. So looking here, I might think that, okay, well, if this is my pattern, right there, I might start to plug this in here, where I would start. I'm not exactly sure what I would start at. Maybe 1. Looks like I start at 1, and then times negative 1/3 raised to the I. That's the generic geometric sequence. A1 R to the n minus 1. So that would be my A1, and then I multiply each time. If I were to plug in 1, let's see if that works out. If I equals 1, I'm going to get 1 times the negative 1 to the 3rd to the I. I'm sorry. This is to the 1. So then I would get 1 times negative 1/3. My answer would actually be negative 1/3. So I equals 1 is not going to be correct, or my pattern is not correct. So there's two different ways I can deal with this. One, I can say that this actually starts at 0. Let's try that. Because if I had I equals 0, then I would have I times negative 1 to the 3rd, negative 1/3 to the 0. Negative 1 to the 0 is just 1. So I get 1 times 1, which is 1. And that would be correct, since my first term is 1. So that is one way of dealing with this. I could have I equals 0 times this. And in that case, I would need to figure out, notice how this does not have an ending to it. So that means I do not actually go up to anything. So I can either put n, so that it just goes on up to n, or you could say that it's actually going to go forever, and you could say that it goes to infinity. The other way you could approach this is if you wanted to keep 1 negative 1/3 to the I, where you start at 1, the other way to shift over 1 is to subtract 1. Then if I had I equals 1, I would have 1 negative 1/3 to the 1 minus 1, which ends up being 1 negative 1/3 to the 0, and that goes away again, and it equals 1. So that is another way to do that one.